Today we are working through Chapter 7, Introduction to Probability. And in particular, and these are kind of notes to myself of things I need to cover. There's a lot of different bits and pieces in this, so let's get right in with there are essentially three kinds of ways in which people calculate probabilities. The first one are relative frequencies. So you can use this way of calculating probabilities where you collect data and you put it into either a table, and very often you then convert them into relative frequencies. I'll show you an example of how you might do that. So let's suppose, I guess that should be 1. Let's suppose you collect data on a large group of people and you find out how many are in the family. So some of them are a single child, and to make my life easy, there's only 6 here. And these are the kinds of answers that you got. So you got 15 of these and 25 of these and 30 of those, 20 of those, 50, 60, 70, 80, 90. Nobody there and 10. There's quite a random kind of list. This is a frequency table. And if you wanted to use this to calculate a probability, you might get a question like this. If you choose one person at random, what is the probability of the following events? So first thing I'm going to do is make sure I counted these right. 20, 30, 40, 50, 60, 70, great. A very nice number to calculate with. There's 100 people I could choose. So let's suppose the first probability is, what's the probability I choose a person that has 3 people in their family? Well, that's 30 out of 100. And if they want the answer as a fraction, it's 3/10. If they want the answer as a decimal, it's 0.3. And if they wanted it as a percentage, it would be 30%. So there's a 30% chance that if I choose one person from this group of 100, that they're in a 3-person family, right? They get them and 2 brothers, whatever. You can also use it for questions like, what's the probability that you choose someone and they have 4 or more in the family? Well, the bottom number is at 100. And don't you just count whoever it is that you're counting, right? So 4 or more would be those, and those. And I'm really not being very good at getting questions that have different answers, but sheer coincidence, isn't that also 0.3? Now I could say things like, what's the probability that it's not 2 in the family? So if it's not 2 in the family, aren't I counting everybody else? Agreed? And if you do that, there's 75 of them. And that would be 3/4 or 0.75 or 75%. And you could also get, what's the probability that it's between 3 and 5? I always wonder about 3 and 5 because do you include 3 or do you include 5? Isn't that a kind of English language choice? When I say between 3 and 5, I mean including 3 and 5, right? So will we just take it that's an unsaid rule, right? That between 3 and 5 means that. So you add 3, 4, and 5 together, and the answer you get is 50 over 100, which is a half, or 0.5. What's the probability that you pick somebody from this group and they have 5 siblings? There are 5 in the family. What is the probability? It's in front of you. Yeah, what is the probability that you choose a person from this group and there's exactly 5 in the family?
You wouldn't.
Hope you left 8 space bars, sorry.
You wouldn't?
Right, right, zeros. Yeah, that's the number I was looking for. So it would be 0. What would be the probability that you choose a person from this group and there's less than 10 in the family? Less than 10 people in the family? Kind of trick question. 100%, right? Or 1 if you do it as a number. So that's what a relative frequency kind of situation probability would be. Don't you basically just add various versions of these together, divided by 100, and then make it look pretty? Right. Relative frequency. Now, the second kind is very weak. I would never really do it in statistics, but for completeness, actually, I'm doing C. And that's the personal. I should have probably done that one first. Personal probabilities. Personal probability is when someone just, for want of a better word, says or guesses the probability of something. So if you got a question and it went and said, you were talking to Janice, and Janice said, so there are a 50% chance of rain tomorrow. As someone might, if they were kind of mathematical at least, say that to you, right? Well, if you said to her, how do you come up with that number? Don't they kind of say, well, it feels to me like it is, right? They've no basis in fact, right? That would be a personal probability. So if someone just picks a number out of the air and says, yeah, there's a 99% chance that that boyfriend and her are never going to make it, right? That's not based on, well, I have observed the last 500 boyfriends that she had, and this was the percentage that made it, right? It's not based on any scientific thing, right? So personal probabilities are what someone says they are, and there is no evidence to back it up. And so I'm not going to spend a great deal of time on them because they're pointless. Couldn't you be a good guesser or a bad guesser? I mean, who knows how good your guesses are? Now we'll do the theoretical ones. Now, in theoretical probabilities, which are actually some of the most common, and we did a lot of them on Friday. Remember the card ones and the dice ones? They all count in that group. So we've kind of covered them, but just a couple of examples. The probability that you roll a single dice and you get, say, an even number. Well, there are 6 numbers on a dice and 3 of which are even. So the probability would be a half or 0.5. And if I was doing a card one, you might get, what's the probability that I get an ace? In that case, there are 4 aces out of 52, which simplifies down as 113. I'm not going to turn that one into a decimal, it's really ugly. Can you remember those probabilities with the 2 dice adding up to 7 and rolling a dice and it's less than a 5 and face cards and all that? They kind of belong in that group called theoretical probabilities. So are we all comfortable with, you get a table where you collected the data and then you use this table, a frequency table, to calculate probabilities, right? That's relative frequency. Your friend Janice just tells you what she thinks it is, personal probability.
Well, that's the death is just a guess, or
Well, you sometimes they've got a hunch, but they can't really put it, they can't justify it. You know how like you might say, I don't know.
how could I write that down? I don't understand why I write it down.
Well, you just write it down your own English. Personal probability is an estimated probability based on just a guess.
Okay.
I don't think a personal probability is very strong. I mean, some people are really good at guessing, aren't they? And some people are absolutely hopeless. And I don't know which one the person in the story that they're talking about is, right? Now, if you're a really good guesser, if that's the right word, wouldn't you probably be a really good gambler? Yeah, you're playing cards and you think, I think I've got a better hand than them, right? You've no evidence because you can't see their hand, right? But you're guessing. Don't bet your fortune or your house on that. And theoretical is actually the best, most accurate way of calculating probabilities. Okay, so I'm going to calculate some more but probabilities in a moment, but I think it's time for me to show you some homework questions. I don't remember if I showed you any last time. So let's show you what they look like. Make this a little bit bigger. Okay, here are some examples of probabilities. Did I do any of these last time? I can't remember. Okay. Is 0.55 a legitimate value for a probability? Yes, that's the end of it. And no, pick one of the reasons for why it's a no. 0.55, yes or no? Right, it's in the range, you can do it. Is 0 a probability? Yeah. What about 1.15? Could that be a probability? Isabella, tell me which one of those three dots then is why it's a no.
It's no, the probability cannot be greater than 1.
Great, remember range of probabilities. 1 or 100%, I guess, if they've done percentages. What about D, yes or no? Careful. Can you have a probability of 1?
Yeah.
Yes. Right,
Yeah,
0,
100%.
100% or 1, 0 on the other side. So it's a yes. Now, what about negative 0.35? That's a no. And the reason that is probabilities are never allowed to be negative and they're never allowed to be bigger than 1. But they are allowed to be 0 and they are allowed to be 1. Right? Agreed? That's the range. If you want to do it as a decimal, 0 to 1. If you want to do it as a percentage, 0 to 100%. Right? So as long as a little percentage behind it, it's okay. Now, in question 2, suppose that you live in a city where 126,000 households and a polling company randomly selects 850 of them. What is the probability that they pick your house? Well, that's technically a relative frequency. It's not done theoretically, it is actually physical houses, 850 out of 126,000. And yes, that is the correct fraction, agreed? 850 out of 126,000. But that's not the answer that they want, because isn't there a rule that fractions should be simplified? So I'm going to do that right now in my calculator. 850 divided by 126,000. Doing a math fraction, and it is equal to 17 out of 2520. Now, isn't it great that calculators can deal with simplifying fractions, especially when they're horrendously big numbers, because you could be there all day doing that. So far, so good? Right. Now, A car dealer has noticed that 4 out of 25 new car buyers return their car for some warranty work in the first month. That's quite a high percentage, but you know, it's under warranty, so it won't cost you much. So you know the kind of thing, you buy the car and the front rear light doesn't, you know, blink, right? Or the seatbelt sticks, right? You know, there are 1,000 things in a car, right? So it's not a surprise that something's not perfect, right? So within a month, people go back and say, you want to fix my driver belt, say it's sticking, or you want to fix that blinker, it's not blinking, or whatever it might be. Now it says, write a sentence expressing this fact as a proportion. Well, could be this one. A car dealer will notice that 4 out of 25 new will return their cars for warranty work within the first month. Okay, I like that one. Okay, I need help here. What is the difference between .2 and .3?
So .2 says that they're not going to return their cars for warranty work, whereas the third one says,
Oh God, I never saw the word not. Okay, I've used this excuse before, but shouldn't you always read the question carefully? Right, that's just what that is. Okay, now they say write it as a percentage. Well, wouldn't you take 4 out of 25 and turn it into a percentage? And write this as a probability. Okay. A car dealer has noticed that the probability is 4/25 that a new car will return. So, oh, that was pretty stupid of them. Didn't they make it the third dot in each question? They could have at least jumbled them up, you know, so you had to read them, but whatever. Now, here is a kind of question where they ask you just to tell, is this a relative frequency or is this a personal opinion probability, right? So here we go. And then it goes on and says, how do you think the probability was determined? Right, how was it calculated? Now, according to Krantz, the probability, oh, there's a little reference here. So if you go to a book called Krantz, published in 1992, and you turn to page 161, so that's just a reference. The probability that a randomly selected American will be injured by lightning. So there's something. This guy, it must be a guy who just collects probabilities, right? This guy figured out that 1 out of 685,000 is your chance of being hit by lightning, at least injured by it. Wow. Now, is this a personal interpretation, or do you think he got it from data?
Unless he's using a really broad definition to include just being in structures hit by lightning, I don't think that's accurate.
It may not be accurate, but the question is,
I mean,
which
sorry,
of the two types? Is this just his personal opinion, or do you think he's
that's what
collected
I mean,
numbers?
I think it's his personal opinion.
Oh, I would disagree with you. And the reason the reason I'll disagree with you, I think the fact that it's published, right, and it's a scientific place where you can go and look, tends to mean that it has data. Scientists don't publish papers that say, I think the sun orbits the Earth, because that's my personal opinion. Whenever they publish something, they've collected data or evidence. So that's why I'm going for it's a relative frequency. And then there's two choices here. Either the third dot or the fourth dot. I wonder if I can make that bigger without making it wrap. Okay, that's a little bit better. So let's look at it. The third dot first. The relative frequency interpretation of probability applies here. The probability was most likely determined by observing the number of Americans injured by lightning during a number of years and dividing it by the average population. I think that's how you came up with that number, right? And this choice, the relative frequency, the probability was more likely by the transpersonal experience. So I am going with that one, not his personal experience. Hopefully you agree with me. Of course, if I'm wrong, I will still disagree with Webberstein because I think I'm right. Now, how about this one? According to my neighbor, the probability that the tomato plants that she planted last month will actually survive and produce tomatoes is 1/4, right? So 1/4 of the things I plant, I'm going to get some tomatoes off them. I guess that's what she might be saying. Would you agree that's a personal interpretation? And how would you come about it? Well, the probability was most likely determined from the neighbour's previous experience of planting tomatoes. Or, I like that one. Let's see what the other one is. Is by the neighbour observing the number of tomatoes planted in in other people's gardens. I'm more likely to go for 3. Would you agree? She probably talked about her tomatoes because aren't there so many variables like, well, I water my plants a lot and I look after them, but I don't know what the other people do. Maybe they do a better job, maybe they do a worse job. So I'm going to go with 3, and you can argue quite intelligently, I'm sure, if you wanted to choose another one. Now, C, a similar question, but a little bit different. According to the nursery where my neighbour purchased her tomato plants, if a plant is properly cared for, they tell you that the probability that you'll get a tomato is 0.92. So that tells me if this is correct, and we'll talk about what that's in a minute, but if I match it with this one, isn't she a very bad gardener? Because according to the nursery, look, if you feed them right and you put them in the right place and you weed them and you do all the good stuff, trim them, whatever you do with tomatoes, 92% of these guys, 0.92, are going to give you some tomatoes out of them. And she got a 25% allegedly. So she's just a bad gardener. That's what I've decided. Now, the way this information is phrased, it's a relative frequency, I suspect. And the reason I'm saying that is because would you agree that a nursery has a lot more data? They know how many they sell and how many, turn into tomatoes at the end. Now, they might exaggerate it so you'll buy them. I mean, maybe the real answer is only 80%, but they'll say it's 92. And then if you complain, they just say, well, you weren't watering it enough or something, but that would it. So look for the relative frequency, which is 2 and 3, and then figure out which one you like. Now, the probability that a husband will outlive his wife is 3/10. And a little reference from that guy, Krantz. So that guy must have collected a lot of data about everything. I'm going to say that that is a relative frequency again. So now we have to figure out how he came up with this 3/10 answer. The probability was most likely determined by observing how many US couples there are and noticing the proportion of couples in which the husband outlived the wife. I think that would be how you would do that. Let's see if the third dot has a better chance. And that's determined by someone's personal experience with couples they knew where the wife outlived the husband. So he's just saying, well, I know about 10 couples and 8 of them, the woman outlived the man and the other 2 it didn't. So I'm much happier with that as a scientific one. I'll let you play with that one. Same idea. And now we're on to calculating theoretical probabilities. Let's do this one, then I'll return to my notes and we can do some card games. Casino games are often use a dice, 6 dots. You throw the thing, equal number likely coming up, and that the dice is fair. So the probability that you get 4 dots is 186. To get 3 dots is also 186. And to get an even number is 386. Any of those answers need to be changed.
C should be 1/2.
Yeah. Remember, unwritten rule, all fractions should be simplified. And this question wants your answer in fractions, so that's what you give. If they wanted it in decimals, they would say to 2 decimal places or something, right? Now,
I have a real quick question.
yes.
On the second part of that question, was it asking for each of 1 or 3?
Oh, I missed the word 1. I only saw the red 3. So technically, isn't that 2 out of 6 then? Because it's 1 or a 3. Yes, welcome. So in question 6, it was 1 or 3 dots. So that's a 1 or a 3. So there's 2 chances out of 6. Okay, so let's work on
That's 1/3
probabilities.
then, right?
Yeah, and that simplifies to 1/3. Correct. So let's do some card ones. We're going to talk about the words and, or, and not. And they occur in probabilities quite a lot, right? And so we have to understand what they mean. So I'm going to do the card one because that's the one I'm most comfortable with. So if I said to you, what's the probability that you get a king or a 10? There are 52 cards in a deck of cards, right? And what's the probability that I choose one card? So I should say this is true for every question now, so I won't say it. Choose one card from a deck and you get a king or a 10. Okay, would you agree there's 4 kings and there's 4 10s? Okay, 4 kings and 4 10s. So 4 add 4 gets you 8 out of 52. Are we comfortable about what the word or just means? It's one or the other, right? Now that simplifies down, and I'm taking no chances here. I'll just let the calculator do it. It's 113. Now here's an example of an and being used. What's the probability you pick one card from a deck of cards and it's a king and it's red? Although that might not be good grammar, questions do get written with the word and. So what they're talking about here is both, right? There's 2, like, yeah. So they're really, I mean, another way, a better English way of saying that is, what's the probability of getting a red king? But you see they phrase it with the word and. And so that's 2 out of that, which is what, 126. Now you might get a question like this. What's the probability that you pick a card, one card, and it's not a king?
Is it 48 or 52?
Now, you could simply count all the kings that are not, all the cards that are not kings, and there are 48 of them. Or couldn't you just simply say, well, there are only 4 kings, so that means the rest is 48. you know, kind of do it that way. Isn't it a little bit quicker than counting all the queens and jacks and aces and so on? Now, are we comfortable then that not and or, what they mean in the context of picking a single card, right? So now we're going to make things more difficult. What's the probability that you get a king or a red card? Well, I'm going to deliberately do this wrong. You might, and it makes sense, but it doesn't work, to say there are 4 kings and there are 26 red cards. So the answer should be 30 out of 52. And I said that's wrong, and it is. I call this double dipping. That's not its real name, but I call it double dipping. Do you realize that we've counted some cards into 2 times? Right, we've double dipped. How many cards have we counted twice?
2.
2. And so the correct answer isn't 30, it's actually 28. And now I'm going to simplify that fraction. And I get 7/13. Now, do you notice in this question, you added the 2 and got the answer? And this question, you added the 2, then you took away the double dipping, right? So doesn't it really depend on what these are, whether you just add them or add them and take away the overlap, right? And we have a name for those 2 situations. And here is the name. They are mutually exclusive or not mutually exclusive. So a king and a 10. Let's look at those 2 guys. They are mutually exclusive. What that means is they share nothing in common. Would you agree kings are kings and 10s are 10s and there's nothing connecting them, right? They're separate things. So mutually exclusive would be 2 groups of things that share no common terms, right? There's nothing in common. Does that make sense? Mutually exclusive, the fancy word for meaning that. Now, if I'm talking, so these are, and these are not mutually exclusive because a king and a red, they are not mutually exclusive. Would you agree that some kings are red and some red cards are kings, right? There's an overlap there. If there's an overlap, won't you have to take care of the double dipping? If there is no overlap, right? If they're mutually exclusive, can't you just add them together? So you will look at 2 events that have an or between them, and you will say, they are mutually exclusive. Great, just add the first one, second one, done. Oh, they're not mutually exclusive, right? Add the first one, add the second one, and take away the both, right? So let's show you what that would look like in a kind of formula. If A and B are mutually exclusive, the probability of A or B is simply just the probability of A plus the probability of B. You just add them together. And if you think about it, isn't that 452s add 452s? Now, if A and B are not mutually exclusive, like this situation, then the probability of A or B now becomes the probability of A plus the probability of B, and then you take away the probability of them being, of both things happening. And a little bit more formal than that, the probability of A or B is the probability of A plus the probability of B. And instead of both A and B is what the probability of both are, right? If I say to you, what's the probability that it's a king and a red? Don't I mean both? So we have two different formulas. When they are mutually exclusive, you just add the two together. And when they are not mutually exclusive, you add the two together and then you subtract, you know, the double dipping part. Now, in normal calculations, they look like a single fraction. And the reason for that is, aren't all of them going to be over 52? So you don't need to say 4 out of 52 plus 26 out of 52, take away 2 out of 52, which is what that formula is saying. Since they're all out of 52, can't you just do one big 52? And it's the same event. So this is a bit like the A's, the B's, and the take away the both, right? And this is like the A's and the B's. And that's all you have. Are we good so far? Right, let's do some more card ones in. I was going to do some more of the dice one, but I threw away my dice and I ain't doing that table again. So sorry about that. So what's the probability that you get a face card or 10? Okay, so we're talking about ors again. A face card or a 10. Okay, are face cards and 10s mutually exclusive? If you're a face card, you can't be a 10, and if you're a 10, you can't be a face card. Would you agree? Yes, mutually exclusive. So don't I just need to find out how many of these there are plus how many of those? Right, well, I know how many 10s there are. Can anybody remember how many face cards there are in a deck of cards?
12.
Yeah. Jack, Queen, King, 4 times 12. So this fella becomes 16 out of 52, which is 4 13s. Now I'm going to do 2 ors. Here's the first one. What's the probability it's a face card or a black card? Now, are they mutually exclusive? No. Aren't there some face cards that are black? Aren't there some black cards that are face cards, right? So, in a deck of cards, there are 12 face cards. In a deck of cards, there are how many black?
26.
26. Now take away the both. How many face cards are black? How many black face cards are there?
6.
We sure? How many black face cards are there? Yeah. I'm saying, are you sure? I had to check in my head. You are right. And in this case, then, I believe you get 32 out of 52, and that gets you 8 out of 13. Yep. Yep. Okay. So what's this one? And it's a trick question.
Wouldn't it just be 12 because a face card is a king?
Yes. Do you see in that one, you kind of short circuit the equation? It's a kind of trick question. Right. What's the chances of being a face card or a king? Well, if you are a face card, aren't you already a king? So you don't need to worry about it. Isn't it just getting a face card? Now, if you wanted to set that up, I guess it would be number of face cards 12 plus number of kings 4. Take away the number of kings which are face cards, which is also 4. So if you wanted to set it up, can you see it's still 12 out of 52, but
Would that be mutually exclusive or it's the same
Oh,
thing?
those guys are not mutually exclusive. Aren't kings face
Okay,
cards?
okay,
And some
okay.
face cards are kings. What is special about this one isn't the double dipping the exact same thing as how many kings there are. So you could either just realize that and jump right to the answer, or you could say number of face cards 12 plus number of kings 4. Take away how many cards are both kings and face cards? Well, that's just 4, isn't it? Because all of them are face cards. Yeah, all the kings are face cards. Sneaky. Let's do some ands then. And I'll do some, well, I'll start off with a nice one. So, how many kings are both red and kings? Which is just another way of saying red kings. How many red kings are there? 2. What's the probability that you're a king and a face card? Trick question.
4.
Correct. Why?
Because there's 4 kings in a deck, and they're also face cards.
Agreed. If I say to you, you're a face card and you're a king, right? And you have to be both. Doesn't that just mean you have to be a king? Now this one is also a trick question. How many cards are both kings and 10s at the same time?
None?
Would you agree that kings and 10 cards, right? So if you are mutually exclusive, won't the probability with an and always be a 0? If you have 2 events and they are mutually exclusive, won't the probability of first thing and second thing be 0? So as a formula, it would look something like this. If A and B are mutually exclusive, then the probability of A and B will be 0. Does that make sense? That if you're mutually exclusive, there are no guys who are both. Because isn't that not what mutually exclusive means? Doesn't it mean the exact opposite of that? You share nothing in common. For a few moments that we have left, we're going to look at what's called complementary events. Suppose you have an event A. Its complementary event I believe in this textbook, they put a little subscript, capital C above it. And that's what you write when you want to say complementary. You will find in other textbooks, so I'm just putting it here. You might see that notation, right? I'm never going to use that notation, but just in case you watch a video and you see this or this is less likely, but you might see this for sure. And definitely I've seen this. It means the same thing, it's just a different symbol. So kind of crossing them out and making them go away so that you don't focus on them, because that's the only guy we're going to use. Well, right, so event A, it's complementary of a event A called complement of A, or AC for short, is all the things that are not in A. So if A is I get a king, won't the complement of A be it's not a king? If A is I've got a red card, won't the complement be I got a black card? If A is I get an odd number in a dice, won't the complement be I get an even number on my dice? And there is a lovely little formula that we've actually used once today. Remember the one about not being a king? You could just add them all up. That was actually using that result. So here is the property that can be used. If you find the probability of an event A and you add the probability of getting the complement of A, right, not A, what does it always add up to, would you think? It's always the same number.
$100.
100% or 1. Does that make sense that everything is either in A or it ain't in A, regardless of what A is, right? You can rearrange this then, couldn't you, to find that? Now, what that might look like is they won't do that. They will use the word not A. So if you see not A, it means a complement of A, right? For instance, if I said to you, what's the probability that you pick a card and it's not a king? Well, it's the same thing as that guy. And isn't that guy a lot easier to calculate? So that would be 1 take away 4 out of 52. Remember that 48 out of 52 that we got? I think it was Maggie that got it. That's the formal reason for what she was doing. Were you doing that in your head, Maggie, even although you didn't have words for what you were doing? Yeah?
Yeah.
Yeah. So, time up. Put your last name.